All right. We were a little bit short on time in class to go through this first example, so I wanted to record a video to make sure you can go through that in detail and rewind and watch parts as you need. So our goal today is to go through kind of a first or a basic vanilla neural network and how to set it up in PyTorch. Um, we're going to assume that you familiar with Python and at least kind of basic object-oriented programming in Python. There isn't really much you need, but PyTorch does make use of a little bit of that. So it'd help, if you haven't seen it, it's okay. Just go look at like some simple examples, kind of a quick primer, and that'll be good enough for what we need. But I also assume that you've installed PyTorch and Python. So let's get going. I'm on the PyTorch website. We're going to look at their little quick start here. We're not actually going to do things quite the same. This one is set up around a classification problem. And we're going to do a regression problem as we've been discussing in class, but we'll pull some things from here and make some connections. You might also want to look at this tensors tab here. The summary version I'd give is that uh, NumPy, you still use NumPy, but when you bring data into PyTorch, it needs to be in a PyTorch tensor. This is a torch.tensor. And you can do that directly from data or from NumPy. It doesn't copy, it uses the same memory, so it's efficient. And a torch tensor operates a lot like a NumPy array. It has a lot of similar functions like ones like, ran1, zeros, math, indexing, shapes. There's a lot of mapping. It's not exactly one-to-one, but a lot of things map over. But it needs to be in Torch, one for backpropagation, so we can compute the derivatives. Torch isn't going to be able to compute derivatives for NumPy, so it needs to be in a Torch tensor, and also for GPU usage. It's already GPU ready. So you're going to have to get things into Torch tensors. Like I said, it's more or less similar to NumPy, but we kind of bring things into NumPy, and then when we're done, sometimes we bring them back over to NumPy. Anyway, so let's go through this quick start. I'm going to skip the data part for now, or let's get to the more interesting part and create a neural network, and then we'll come back to the data at the end. So we're going to import Torch. We're also going to import the module NN neural net because we're going to use that a lot. You can see there's NN dot, NN dot, NN dot. I don't want to keep writing torch.nn dot, just save me some time. And so we're going to create a network. So we'll create a class. Again, this is kind of a basic object-oriented thing that you might want to review if you haven't seen this. You can call it whatever you want. I'll just call it vanilla network. And we're inheriting from nn.module. Okay, so we need to inherit from that. And every class can have an initialization function. It's always going to have self as the argument. We're going to want to call the superclass, especially because we're inheriting from something here. Call superclass, call its initialization function. So you can think of this as just boilerplate. You're always going to have this, okay? It's just a regular class thing. And then we do whatever else we want to do in here to initialize. To initialize, we're going to create a nn.sequential. That's just going to call or define a set of operations that it's going to do sequentially. So in this case, it's going to call a linear layer, and then a ReLU layer, and then a linear layer, and then a ReLU, like the outputs of one become the inputs of the other, and so on. Just stack them together in a sequential way. So let's do our own. We are first going to call a linear layer, and I want to put the number of inputs and then the number of outputs in this linear layer. And I know that the data set that I'm going to use in this example happens to have 13 inputs, so I'm going to put that in here, and then I can put whatever outputs I want. If I put one, I'd be done, right? Because I should say this example also has one output. I'd be done. There'd be nothing to do. I'd have no nonlinearity. This would just be linear regression. I guess I could do that. That's not going to be super interesting. I'm going to want to add more layers. So let's say I made this 24. And just pick up a number. I can't do just that, remember, because if I just add linear layers together, then that really accomplishes nothing, right? This is just equivalent to that original linear layer. So I need some sort of nonlinearity. So we can add a tan H or exponential ReLU, or sorry, exponential linear unit. But we'll just use ReLU for this example. That'll work just fine. I got to comma separate all these different layers. So this right now would be 2 layers, right? Because I started with an input. I now went to 24 neurons or nodes, and this number's got to match this number because I'm going in and out. I mean, it wouldn't have to if something weird happened and something different happened in here, but because this is just a activation, it's going to operate element-wise on everything. This number needs to match this one. So I've got one hidden layer output. So this is just a 2-layer network. Let's add some more. I can add as many as I want, right? But let's just not go too crazy here. Let's keep it pretty simple. And I'm going to go from 24 to say 36, and I got to keep those numbers the same and then back to 1. So I went from input of 13 to a hidden layer of 24 to a hidden layer of 36 to my output of 1. So this is a 3-layer network. And this is where, a lot of the magic or dark arts or whatever you want to call it, experimentation of changing hyperparameters here is like, how many layers should I have? What nonlinearity activation function should I use? What should the width of these be? And how should they change? And we'll see much more variation than this. This is just a basic network. So I've defined it. I want to save this in a variable. And again, in the object-oriented world, I'm going to put this as an instance variable so I can use it in other functions within this class. So I'm going to call it self.network. Call it whatever you want, but that keyword self, right, is part of this object. And then I always define the forward function. Forward function is when you actually call the model with an input. Initialization is just what happens when you create this network. Nothing is being passed in yet. You're just initializing things in it. The forward is what happens when I'm actually passing in an input. And in this case, all we do is just call, is what I needed to save this into a variable name I could use. Just pass the X in, and that's it. Okay, so that's all for my network. Simplified, I didn't need these flattened things. They're using this because they're doing like an image thing and they're flattening the image into an array such so they can call these linear layers and whatnot. And we're going to ignore this device stuff for now. We'll come talk about that later. But in brief, this is just to allow me to move things onto a GPU. So right now we're just going to keep things on the computer, but device is a word used in the GPU world. And so this is like to check, is CUDA available? Choose CUDA here, MPS. This is Apple's Metal, which I could use, but I'm not going to. So we're just going to ignore that. And so notice that they moved things through the device here, which we're also not going to do. That's important because it's copying over that data over to potentially that GPU. And the way they've written here is nice and generic so that you could just keep it this way. And depending on what you have available, it will just automatically take care of that. But that's fine. And I'm going to do what they did. I'm going to initialize it. I called it something different. I called mine vanilla network. So this is now calling the init function because I just initialized it. And later, if I passed, an input in, this would call the forward method on that object, but we're not going to do that right now. So I don't need to do the to device. There's my model. I could print it out right here like it shows. It will kind of show things. These have biases. You could turn biases off. It shows you the input output. And this has already initialized everything for me. So behind the scenes, it created a weight matrix here that was 13 by 24. This one was 24 by 36. It created the 24 biases and so on. All done for me. You could also pass other things in here, right? Like I could, for example, might not want to hard code any of these numbers. Maybe I wanted to make the number of inputs a variable, and I want the number of outputs to be a variable, and I want to pass those in here, right? I want to set them up in my outer script and call this 13, this one 1. I could change them more easily, and then I would use them here, for example, and I could change these, or I can make it the same. I can do all sorts of things, right? I could put in the number of layers, do a loop, all sorts of things, but I'm just going to hard code it, keep it really simple for now. Okay, so there it is. Again, you can mess with these widths, activation functions, all sorts of things. So I've defined my network. Yeah, that's all I want to say. Well, let's see. What else was I going to say about that? I feel like there's something else. Maybe it'll come back to me later. So yeah, we'll keep going. After defining the model, I need to define the loss function thing I want to optimize on. And I also need to define the optimizer that I'm going to use. So let's just kind of copy this example here. Except for we're not going to use cross entropy loss. That's appropriate for a classification problem, which is not what we're doing. We're going to use a mean squared error, as we've talked about, is a good one for regression. So let's see if we can autocomplete because I can never remember. Okay, MSE loss. So it says I want to use mean squared error loss. And the optimizer I want to use, I got to define that as well. They're using, we talked about gradient descent in class, and they're using a variant of that, stochastic gradient descent. That's the one that's going to batch, um, uh, generally even down to one sample. But anyway, stochastic gradient descent, could use that. SGD. I am going to actually change it. I'm going to use Atom. That's kind of a go-to default. It's a good one to use. We'll talk about it later. I think it's going to work better for this problem. So we're just going to use it. But you're going to pass in now the design variables, the things you want the optimizer to be able to change. And there's a convenience function for me already. I have to call it model because that's what I called it here, but this network thing, if I call the parameters function on it, it's going to return a list. It's actually not a list, it's an iterable, but think of it as a list of all those weights and biases. It's just going to return them, make them available, or pass them to this optimizer so it knows what to change. And then LR, here's my learning rate. More than -3 is not a bad starting point. This is another hyperparameter you want to mess with. Learning rates that are too small will take forever to train, and they'll only take tiny steps, and they might not explore well if you have, local minimum or probably more likely saddle points. If it's too big, you're going to be jumping around too much, and you might not converge well or at all. Okay, so something to play with, but this is for typical scaled problems, probably a good starting point. Yeah. Okay. Let's keep going. So I've got a network set up. I've got my objective set up. I've got the optimizer set up. So I'm going to set up a training loop. So I'm going to copy this function and I'm going to simplify it quite a bit. I don't need everything here. So let's see, what do we don't need? I'm not going to do this device thing because we're not going to worry about GPUs for now. I'm not going to do this printing. This is useful. Here it's like printing every 100 batches. This is useful if you got a lot of data, especially a lot of batches in this case. And you want to see how things are going periodically. You don't want to see how it's going every single batch. We need a small data set, so not important. So we don't need that. Just need to grayed out. And we don't need to turn this into a numerator because I don't need to know which batch it is. So we'll just simplify it even further. Okay, so what do I got? Okay, so in this function, I'm going to pass a data loader, which I haven't talked about, but that's where my data is coming from. We've already defined a model. That was my network here. We've already defined a loss function, and we've already defined an optimizer. So I've got those things. This doesn't have to be in a function. You could take these steps and just put them in your script. But it's nice as a function because I can reuse this. If I write it in a general way, like this is, I can pretty much just keep using this. I mean, we'll change this as we get fancier, but for a vanilla neural net, I could play with different architectures here, different loss functions, different optimizers, different data sets, and I wouldn't have to change anything in here. So what are we doing here? First, we put the model in training mode. Just something to remember, like this training mode versus evaluation mode is going to do some things we haven't talked about yet. It'll do things like turn an evaluation mode will turn off, like drop out, batch norm, and things like that. Things that you only want to happen in training. Don't worry about it for now. Just remember, we want to turn this on the training mode when we're training. So this is just always going to be here. For data loader, you don't have to use a data loader. It's a convenient thing, and you'll see why. But you could just iterate. You could just give it a matrix or some lists of data. Just run through a loop. This loop is going through batches. So you could even not have a loop here. Maybe you just give it the whole data set at once, and you just want to do a step each. This train function is not meant to be training the whole thing. This is meant to be one pass of the data or one epoch. So you can just give it the whole data set and you wouldn't have to loop at all. But this data loader is going to be set up so that it can do batching easily. This is automatically doing these batches for us. So this is one batch of data. And the capital versus lowercase is just to signify the typical use case where X is going to be like a matrix because there's going to be many inputs. It's one dimension and then many data sets, right? These are the, say there were 64 elements in your batch, 64 data sets would be 64 this way, and then the number of variables. And Y could be many variables, but often it might be just one output that you're predicting. So this might be a vector, one output, but many data points. So anyway, obviously this is code, so it doesn't care. That's uppercase or lowercase. That's just, kind of a visual reminder, so to speak. Not important if that didn't quite make sense. But so what do? We take the input, X, we pass it through our model, which we've defined, right? So now this is calling that forward function. It's going to go through all these layers, and it's going to spit out a vector of numbers, one for every data point. And I'm going to pass it to my loss function, which in this case happens to be a mean squared error loss, but we've written in a generic way, so it could be any loss function. And we get loss. And notice I'm calling a function on it. So this loss here is actually not a number. It's just an object here. And so I can call a function on it. I call back propagation. We briefly touched on this on class. This is how we're getting derivatives, gradients. We're getting all the gradients through our loss function. So this is calculating the derivative of my loss with respect to all of those inputs in the model, in my network. And now that I have a direction, depending on which optimizer I'm using, it's going to decide what direction to go with that information. And based on the learning rate, this could be a number, it could be a function or whatever. But in this case, it's a fixed number, pick a step. And then we have to zero things out. We do that because it's updating that gradient in place. And so if I don't zero it out, it's just going to add the gradient to the last one and keep adding it. It's doing it in place because that's more efficient to not be creating new memory every time. So again, the nice thing about this is that this is written in a generic way. I basically don't have to touch this. We're a vanilla network. I can reuse this. I can play around with different loss functions, different networks, different optimizers, learning rates, and just keep this the same. Okay, so that's the training function. We've talked about in class the importance of having a separate test set so that we don't overfit. And we can see how we're actually doing on the thing we actually care about, which is predicting data we haven't seen. Of course, the training set should do well, but we want to see how it does with the testing. The testing, you'll notice the inputs are almost the same, except we don't have an optimizer. We're not doing an optimization in the test set. We're just taking the model that we've trained or partially trained, at this iteration, seeing how well it does so far with different data that it hasn't seen yet, that it's not optimizing on. So let's again also simplify this. It's counting how many are correct because it's doing a classification problem. We're not needing that. So it's not just counting only a loss, but like how many it classified correctly. So here it's printing some stuff out. We'll print out, actually, I won't mind printing out the test loss. That's often useful to do. So we'll keep that. Get rid of the device part again. We don't need that. And then let's reorder that so it looks similar to the last one. Okay, so let's see, what is this doing? Yeah, this would be good enough here. So here's a test function. So first we set it to evaluation mode. Unlike training is in training mode, evaluation mode is going to turn off some things that we don't want in testing. Again, we haven't really talked about what these things are, things like dropout and whatnot, but just know like we want to turn them off for testing. So we should put this in evaluation mode. Let's ignore this for now, and let's just look at this part. So it's doing the same thing. We're iterating through the batches of the data, which again, you wouldn't have to iterate if you just wanted to do all the data in one pass. You didn't have a ton of data. We're evaluating the model. And even though this looks the same, this data loader is a different data set, right? This data loader is for training data. This is for testing data. So now we're evaluating the model on the test set. And now we want to see how it performs with our loss function. And remember, what we get out of there, this loss is not a number or a vector or anything like that. It's just it's not a number, I should say. It's an object because we can call functions on it. So if I want to get the actual number out of it, I got to call this item thing. So here we're pulling out the number. And what we're doing here is we're trying to calculate our average test loss. So if I had just one batch, this would just give me the test loss for all my data in one pass. But because I might have many batches, I'm just averaging across the different batches. So I'm initializing to 0, adding up the test loss across every batch, and then dividing by the number of batches. So we had to get the number of batches here and then initialize our test loss, and then we're just printing it out. So every epoch, we're going to print out what's my test loss, just so we can see how we're doing, right? As you get to bigger problems on epoch, could take a noticeable amount of time. So you want to see like if things, going off the rails and I need to stop it and make some adjustments. And actually printing out this is useful in the training loss. Let's actually do the same thing. Let's print out our training loss. So we're going to have to, this formatting is a little fancy. You could, of course, just print training loss, and that's it, right? This is formatting it for a certain number of digits and so on. But anyway, we'll use it because we've got it. So we'll have to do the same thing. We're going to have to initialize it to 0. I call it train loss, and we're going to have to save it at each iteration here. We can just do it here at the end. We'll say train loss plus equals loss. I don't need this whole thing because I've already computed that here. So I'll just take loss dot item. I'm pulling out the number, and that's it. And actually, what I'm going to want to do, I'm going to divide by the number of batches to average it. So train loss equals training loss divided by the number of batches. Great, print it out. And I'm actually going to return these losses because I'm going to want to plot them. So I'm going to save them at each epoch. Okay, so I've got a training function, a testing function. I know those got kind of long once I added all the kind of tracking the losses, but hopefully that made sense what they're doing there. Yeah. So let's go back to my main script here. Let's go through a loop. I'm gonna just write that out. So I got to choose a number of epochs, another parameter I can choose here. 5 is gonna be way too many, or sorry, way too few. I don't know how many is too many. I'm just gonna pick 1,000 here. And then I'm gonna do for E in epochs. Sure, I'll print this out too. Why not? It's just printing out which epoch I'm at. In this case, this data set is small, so it goes so fast. I can really see them, but in general, I want to do that. And then at every epoch, I'm going to call my train function and my test function. So each epoch, I take my whole data set, I go through and train, and then I see how I'm doing with my test set, and then I'll repeat again. And so I can watch how things are going and see if things are going well. I don't have these data loaders yet, but I've got all these other stuff. And we return training losses. Something we added here is that I'm going to calculate these or save them. I want to save them because I want to plot them. And probably the best way would be to initialize an array that's of this size and then change this so that I'm indexing. But I'm just going to append them. Let's keep life simple here and a little less efficient, but that's okay. So I'm going to initialize them and then just append them on. Training losses, this is just standard Python, right? Doing append to a list. And then let's do the same thing for a test. Okay, great. So I've got them and I could plot them now. So let's even do that. I'm gonna have to import pyplot, but we'll plot training losses. I want to plot them versus number of epochs. So epochs is a number, so now I'm turning this into an array from 0 to epoch so I can see it. And then let's do the same thing for the test losses. Got a legend, so I know which one is which. Train, test, show. And we better import that. Import matplotlib.pyplot. Okay. All right, so I think that's all good so far. Sorry for my lack of comments because I'm talking through this. So hopefully it makes sense. I'll say one thing is a Python thing, not a PyTorch thing. Probably most of you already know this if you've done any Python. It's good practice to put all my script stuff in this, again, kind of boilerplate stuff, if you will, that says if name equals main. And what that does is that if all you ever do is do things that are just in one file in your whole code that you're running is in one file, and then when you do a different problem, you just do it all in one big file. It won't really make a difference. But what this does is that if you've got bigger projects where you've got multiple files, if I'm calling this file as my head file, this is the main file I'm calling directly, it'll run everything in here in main. Whereas if I didn't have this and I just have this all here, if I import this file into other files, which is what you often do, like here, right? Say I'm importing things, I'm importing stuff. If you're writing a package and you're making things a little more complicated and you import files, this file into another file, it'll run everything in that file, right? It'll load all these functions, but then it'll do all these calculations and it'll plot stuff and print stuff. And you really don't want that happening, right? I would be surprised if I imported Torch and all of a sudden it started plotting and printing all sorts of stuff. So it's just good practice to do this, although this class it wouldn't matter, but good to get in that practice. So let's see, I think that's it for that. So we've got our network defined, loss function defined, optimizer defined. We're now going through a loop. Each epoch, we're training based on all the data in one pass, and then testing, and then going around as many times as we want, continuing to improve. Okay, so we got to do something about our data. So I just grabbed a data set online. This is something to do with housing prices. It's not too important what these represent, but these are like these columns here are different features, different inputs. Some are continuous variables, some are integers, and they represent things like how many bedrooms are there? You know, what's the distance to the nearest school or something like that, density of whatever. Okay. And then this last column is the house price in some sort of units. Doesn't really matter, but I think, yeah, there's 13. So 13 inputs, last column, one output. So let's load that up. Again, test train, those are good. These are going to stay pretty much the same. Load data. This one is probably going to change a little bit more depending on what you're doing from function to function. Sometimes the data preparation is kind of time intensive. It's very important. Not the most exciting thing, but it's kind of a critical thing that you have good data preparation and, you know, are removing bad values. You're kind of normalizing things appropriately and thinking about, you know, what features that are really need to include and so on. So let's read this in. We're just going to use NumPy. So I better get NumPy. You probably use this, what is the function called? It's something from text, load text. This is a simple function. There's a more fancy function called gen from text, I think is what it's called. This one lets you do stuff like change data types, ignore comments, specify different delimiters, right? Like is data separated by commas like in CSV, or is it semicolons or white space or skipping rows? How do you deal with missing values? Do you want to do conversions? But this file that we have here is ideal in the sense that there's nothing missing, there's nothing to convert, there's no strings. It's just really simple. So we can just use load text. And I think I called this file that, and it just loads this into a matrix. So this is going to be just a NumPy array of rows and columns, right? A 2D array here. So straightforward to load. I'm going to want to separate out the features and the targets. So features is inputs, and that's every row, or it's all the rows, but all the columns except for the last one, right? So this is the output. So it's my house price. So I want to pull everything else out. So I want data of all the rows and all the columns up to the last, but not including the last one. Those are my features. And my targets, these are just kind of machine learning names for things. We use often labels for classification and targets for continuous stuff, but regression things, but you know, we normally call them inputs, outputs in engineering. So targets here, that's my last column. So all the rows, and I need the last column. All right, so that's in NumPy format, but remember, as we discussed before, to get it in PyTorch, I need to put it in PyTorch.tensors. So I'm going to pass them into torch.tensors, torch.tensor, pass them in, and that's good. Unfortunately, this is not everything. There's one other subtlety here that can lead to some hard to track bugs. So because I'm going to do, let's see, I'm just open up a Python REPL here. So here I'm in Python. I'm going to import NumPy, and I'm going to define an array. And I just put 1, 2, 3, 4. Okay, that's my NumPy array. I looked at the shape of X. It's 4 comma. It's not 4 by 1 or 1 by 4. So it's actually not a vector. It's just an array. And this is something that's a little different. And PyTorch, the tensors, they're going to think of these things as tensors. So they want actually a dimension 1. And that's because in general, like this targets can have many outputs, right? It just happens to be that I have 1, but I would really like this to be actually a 4 by 1. Otherwise, it's going to get confused. Um, there are some, yeah, anyway. I actually don't know quite what it does, but you'll get some weird output. Your training will look really weird and you won't know what's going on. So just make sure you check that. That's a common issue. So you can do that many ways. You could take X and do a reshape command. So I know this is I could reshape it. I said, I actually want it to be 4 by 1. So now it's going to do that. Let me call this Y. And then if I look at Y shape, you can see it's 4, 1. They look a little differently when they're printed, but it's the same information. One is just an array of 4, whereas the other is a 4 by 1. And that's what I want is the 4 by 1. And sometimes I don't actually want to, I want to save myself a line because it's like, well, okay, I know this is 4, obviously, because I just typed it out. But how many rows are in here? I could go to the end of the file and see. Or I could go and look at the size, but let's say I just want to do that one line and I've got a big data set that maybe it's even binary and I don't see it. You can also do reshape. If I put a -1 here and a 1, what the -1 says is kind of like not quite a wildcard, but it's kind of saying, I want there to be one column, so make this whatever it needs to be to make the dimensions work out. And so if I do this, it figures out, oh yeah, C's got to be a 4 by 1. And you could do that in general. You could do, I guess, I think something like this and figure out, oh yeah, that's got to be a 1. So this is going to be a 1 by 2 by 2. But anyway, that's just something you got to use sometimes. So you can do that. There's also a view command. I can't remember. Sometimes they're exactly the same. Sometimes they're slightly different. But anyway, and I think you could call it on the Torch tensor as well. So I could have put it outside the parentheses as opposed to on the NumPy array. It might be slightly differently named, but I don't think so. They're almost always one-to-one named, similar, same. Okay, but anyway, again, subtle detail, but just remember that if you see something weird, check your data. Did you actually put it in the size that you expect it to be? And it should be something by 1 or something by something. It shouldn't just be one-dimensional. Okay, so those are my features and targets. We're going to put these in a data set. So like I said, you don't actually have to use the data sets or the data loaders that PyTorch has. They're convenient though, for reasons we'll see, because they can do the batching for me. They can do the shuffling for me. And these are all things you could totally handle yourself in NumPy. It's just a little bit of a pain, right? To kind of go through logic and do things that we're going to do a lot and randomize things or break them up into chunks of size 64 and then figure out the remainder of the last one and save it. It's just going to do this for me. So we're going to first put this into a tensor data set. I haven't loaded this, so we're going to have to go load it. But the tensor data set expects features and targets. And that's it. So it expects them to be separated. So I had to do that. Tensor data set I can get from torch utils is that what it is? Utils.data? Yeah, utils.data import tensor data set. And I'm also going to want a data loader here in a second. So I'm going to just do that. And I'm actually going to want one more thing. So I'm going to do that while I'm here. It's called random, not random split. I'm going to want all three of those. So we've already done the data set. But that's not quite a data loader. So we're going to need to put it into a data loader. And to do it in a data loader, we're going to want to separate it. Well, actually, let's first separate it. So I've got a data set. It's got everything, but I want to separate into training and testing. Again, I really should put a lot of comments, but I'm narrating here my comments. Let's separate into training and testing. And I'm going to do that with that random split function. Of course, again, something you could have done yourself in NumPy, but there's a function that will do this for me, so why not? Random split. Let's go look at how to use this. I actually just learned. So, well, let's see. This one gives us example. Random split, I give the data set and I give it training size, validation size. And here they've put in numbers. Um, although I think I can do, so what this is doing, say I had 100 data points, this would be like put 80 here and 20 here if I wanted an 80-20 split. But I think I can actually have it figure that out for me rather than me having to calculate what number this is. Yeah, so it looks like I can, right? So I could do, in this case with 10 points, I could do 3.7 or I could do 0.3 and whatever. I could have it split things up for me itself. And that's what I want to do because that's convenient because oftentimes it's not exactly going to be an integer, right? I've got like 127 data points and I want 80%. So it'll do the flooring operation, all that for me. And it saves me a little bit. That's not hard to do, but why not? This is saying 80% train, 20% test. So let's call this train data set and test data set. Great. Close that. Oh yeah, sorry, this is the data section here. And I'm not really using any of this because they're, first of all, doing classification problem. They're using this kind of classic computer science problem, classifying these images. But we're getting towards this part. This is the only part we're going to use is this data loader. And we already loaded that. So I'm going to create a data loader. The data loader is going to do the batching for me. So now I got data, separating features and targets. Now I've split them up right here. Right. So first I had a data set that, yeah, was features and targets. Now I've split them up into training and testing. And now I'm going to batch them. So I pass in my training data set and I pass in a batch size. And I probably might want to change that. So I'm going to make that an input. I'm not sure if that is the next variable. So I'm going to make it a keyword argument like they've shown in that example. And then this is going to be test data set. And so this is my trained data loader. This is my test data loader. And that's it. I'm going to return those. Yeah. In the homework, I asked you to do another step, but this is important in optimization problems in general and deep learning as well, that for many reasons we'll discuss, you want the data to be generally of order one. And one way to do that is to normalize it by dividing by, normalizing it on a unit norm. So you would subtract off the mean and then divide by the standard deviation. So it had mean 0 and standard deviation 1. That's one way to normalize. There are many ways, but you want it to be of order one. Otherwise, there's a lot of issues if you don't. Imagine the numbers were really big. Well, I won't get into it here because I don't want to make this video too long, but we'll definitely discuss that in class. Uh, so that's something you should do as well. For brevity here, I'm not going to do that, but you could do that either on the NumPy side, just using NumPy functions, So once you've got this data here, even before you've separated it, you could just do it all together, calculate mean, standard deviations, divide things out. You could also do it once they're torch tensors. I will say in general, you often want to save those normalizations because while the normalizations are very useful for optimization, at the end, when you want to interpret the data, it's not really useful for me to see, oh, the house price is 1.06, which is normalized in some way. Like, what does that mean? I want to unnormalize it at the end. So I have to save kind of my normalizations so I can reinterpret what those data mean. But anyway, that's just regular NumPy there. Or like I said, you could do it in Torch. They're similar functions, like they have the same mean function and standard deviation function. I think some of the differences, sometimes some of the functions, they call things different things. I might be wrong on this, but I feel like they call it, what is it? In mean, they would call, like if you wanted to take the mean on rows versus columns, it would be like dimension, I think is what you use. In one of them, DIM, and the other one you would use like, well, I can't remember, but I think they have different keyword names. Anyway, to look that up. And tools like Copilot, ChatGPT, they'd be very good at helping you figure that out too. Okay, so yeah, let's load this up. We got our data, a training data loader and a testing data loader from my data. What did I call this function? Load data. and I need to give it a batch size. And I'm just gonna move this down here. So all my parameters are by each other. Patch size is 64. Let's say we'll do the same as this problem, but it might be something I play with, you know? If they get too big or too, if they get big, if I put this the size of my data, then there's no batching, which maybe is what I want. It's a little more accurate, but it's going to be per iteration, but it's not going to make as much progress each epoch. So again, there's probably a good balance there. And I guess I have to change these since I want to get something different. All right, so with any luck, I think I've got enough to run this now. I've got data and yeah, let's give it a shot, see what I messed up on. Okay, so yeah, I can't find the file. I'm not on the, I gotta go to the path where I save that file. So let's go to, yeah, here we go. And I got another error. Okay, yeah, so if you see this error, it says some things are double, some things are float. So yeah, so here's what's going on. In all of your scientific computing, you've, I would assume, with rare exception, always use double precision. That's the default in Python. It's default in pretty much any programming language that uses scientific computing now. It's been a long, long time since people have been using single precision for scientific computing. We use double precision, 64 bits instead of 32 bits. We call that a double instead of a float or a single precision. Um, However, that's not necessarily true in deep learning. With GPUs, a lot of them are going to be way more efficient and be able to hold more data if we use single precision, just because, you know, they take up less room for single precision. And that's sometimes a bottleneck. We have tons of data, we want to fit more on. And so a lot of GPUs and a lot of deep learning frameworks will default to single precision, actually. So we lose some accuracy, and that's maybe not as critical. So if you could think of an engineering analysis, if I'm at single precision, I'm losing accuracy. As I get to the course of a program, that could be pretty important that the numbers I get are not very accurate at the end, and that's undesirable. But for this optimization, add some sub iteration. If they're not fully accurate, it's okay because I'm just going to redo it again in another epoch, right? I'm iteratively moving forward. So I can get away with a little bit more here. That's not always true in kind of this physics-based machine learning that we'll be doing in this class. Sometimes we actually need that higher precision, so we'll see that. But let's figure out what we got to fix. Problem is, when I create this network, for example, and it initializes all these weights and biases, it defaults to single precision, as I mentioned. So either I have to change these to double precision, or where it's conflicting is the other place where I create data, which is the data that I'm putting in this torch.tensor. So this is coming from NumPy. This is a NumPy array, and NumPy is going to default to double precision. So I'm going to change it here just to do what people might do in a classic non-physics case. We can set the D type. That's similar to NumPy. They have the same kind of thing, D type. And it's, what is it? Torch dot float 32. Oh, it looks like it's lowercase. So I got to do that on both of these. Makes them single precision. Float 64 would be the double precision, 32-bit versus 64-bit. So let's see if that fixes things. None type object has no attribute size. Okay, so I messed something else up. Loss function. Just take a quick peek through here. Did I? Okay. Play better as a live demo because then somebody can point out where I messed up. Give me a minute. That looks fine. I have to narrow this down in a second. Target size. There's a size problem. Non-type object has an attribute size. That's my mean squared error loss. So I must have passed something wrong to my loss function here. This is my training prediction. Y is coming from my data loader. That should be fine, right? Training data loader, test data loader, train batch size. I don't see anything off there. Well, while I'm on it, this is not going to fix the problem, but I should also mention when I do this random split, it also randomizes the data. But if I didn't have to do that, if things were already separated, I can also add this keyword here, shuffle, and that's going to shuffle this data up so that the training is each batch is seeing a random subset. It's not really important I deal with the testing data because I'm going to just average. I'm just going through all the testing data and average it anyway. But here I'm making decisions about directions to go. So I want to make sure that's random and I'm not biasing it towards, some clump of data. Oh boy, what did I mess up? So, well, let's just go through some good old debugging. Let's write some print statements here. See if I can't figure out what I did. What's the shape of this? What's the shape of that? They're not the same. None type object has no shape. Prediction has no shape. Oh, okay. So I didn't return anything. Yeah, duh. So this is saying prediction is a none. So this means this model function didn't return anything. That's because of my forward thing. I just called the network, but I didn't actually return the output of that. So that's silly. Okay, there we go. Things are running. My losses are going down. They're going like blazingly fast. I can't even see anything. Wow, it looks pretty ideal. It's a little bit too simple of an example. So here my loss started out really high because I just started out with, whatever initialization. I have no idea what the weights and biases should be. It's changing the weights and biases, and this is my loss. This is my mean squared error. And what does that mean? It's like take all the data samples as my average error across all the data squared. So it's not necessarily the best metric for interpreting. We probably want to, as we will do in the homework, you know, first of all, unnormalize and also look at like the absolute error, like how much am I actually off in housing prices? But you can see this has gone down tremendously well. And there's some noise as there should be because I'm batching. I'm getting random data, so I'm going to get different random subsets at different times, but still steadily decreasing. I could maybe even go further, but you can see the testing data is also decreasing. So that means it's generalizing well. If the testing data start going back up, it means I've overfit. Okay, so I think that's enough. I think I was going to say one last thing here, real quick. That's enough to get us going. I think should be enough to get you on the homework. But some useful things to know here at the bottom. I don't need to do this because this problem is so simple. I can just rerun it again and again. But in general, I get bigger models and my training might be iterative. For example, like I might run it for a while and then see, oh, it's not making some progress. But I might want to save the progress I've made. And so I change some parameters and then keep going. And I change some parameters, keep going. Or I run it and now I want to do some plotting and I'm going to iterate on plotting and trying to figure out what to do. I don't want to retrain it every time. So when I'm done or periodically, some number of iterations, I might want to save the state of my model. This is going to save all those weights and biases and such, save it to a file. And then I could load it back up. I could reinitialize my neural network and be ready to go. So I could start from there and keep going, or I can just load it up so that I can inspect it and do some tests with it and do some plots with it. So I don't have to run all that training again. Very helpful. And the last thing I want to point out here, this is going to be different depending on what you're looking at, right? What you want to do. But you'll notice a few things here. After I've trained, I want to put it in evaluation mode and I want to turn off, I think I forgot to talk about this line earlier. This turns off the gradient tracking. I forgot to say this here, right? This happens here too, is that this torch.nograd it just means like I don't need you to track all the derivatives for me while you're evaluating this model because I'm just doing testing here. I'm not going to use these derivatives in a loss propagation, a backwards propagation to the loss function. You wouldn't strictly have to have that, but it's going to, it's going to add more computational costs. And yeah, I don't think it should affect things because you're not actually calculating this backwards, but it's just going to be more expensive. So we'll do the same thing like we do in test. We turn to evaluation mode, we turn off gradient computation when we evaluate that model. And then I might evaluate that model at different points. I might do some normalization here. I might plot things, make different things here, right? So anyway, all right, that should be it for today.